Ever wished you had live captions for every video, meeting, or audio stream on your computer, even when the app doesn't support them? In this screencast, you will build a lightweight Python utility that captures system audio in real time and transcribes it instantly on your screen. Welcome! Accessibility is a cornerstone of great software engineering. Today, we are tackling a deeply practical challenge: how to capture audio coming straight from your operating system and transform it into readable text on the fly. Whether you are building assistive tools for the hard of hearing, creating automated meeting minutes, or simply watching foreign language tutorials without native subtitles, mastering system audio interception in Python opens up incredible possibilities. Before we write a single line of code, let's look at how audio data flows through your operating system. When any application plays sound, it sends raw audio buffers to an output device like your speakers or headphones. To capture this live stream without modifying every media player individually, we need to tap into the audio loopback device provided by your system's audio backend. This loopback mechanism duplicates the outgoing playback stream and pipes it directly into our Python script for processing. To interact with system audio using only Python's standard library, we need to inspect what sound devices are connected to our machine. Python doesn't have a built-in sound card library out of the box, so we will use the built-in wave and struct modules to understand raw byte streams, and we'll write a pure Python module check to simulate discovering input devices. Let's start by writing a script that inspects our environment and lists available audio configurations safely. Handling live audio means dealing with continuous streams of data rather than static files. Raw audio arrives as a sequence of numeric samples representing sound waves' amplitude over time. Because we cannot process infinite streams all at once, we chop the incoming audio into manageable chunks called buffers. Each buffer holds a fraction of a second of audio data. Managing these chunks efficiently prevents memory buildup and ensures our caption display stays synchronized with the spoken words. Now let's write a self-contained Python script that simulates receiving live audio buffers and converting them into formatted text frames. Since we are using standard library tools only, we will simulate the audio stream generator using synthetic byte data. This script demonstrates how our application will ingest continuous data chunks, calculate basic signal metrics like volume level, and output formatted caption timestamps. A great accessibility tool is useless if the user cannot read the captions comfortably. We need a clean, non-intrusive way to render text on top of other running applications. In a production environment, this might be a transparent floating window. For our implementation, we will design a terminal-based overlay UI that formats captions cleanly with rolling history, clear speaker indicators, and high-contrast text styling to maximize readability during fast-paced media playback. Let's implement the caption rendering engine. This script manages a rolling buffer of text lines, formatting each incoming transcription fragment so it appears neatly in our display area. By maintaining a fixed number of visible lines, our pseudo-overlay mimics the behavior of modern subtitle engines found in video conferencing and media streaming software. Watch how the text updates gracefully. Turning raw audio waveforms into meaningful words is where the magic happens. Typically, speech-to-text engines use acoustic models to map audio features to phonemes, followed by language models to assemble those phonemes into correct words and punctuation. When designing for real-time live captions, balancing speed against accuracy is critical. We want minimal delay so the captions match the speaker's lips, while retaining enough context to correct homophones and spelling errors automatically. Let's pull our components together into a cohesive processing loop. This script simulates the end-to-end workflow, taking raw audio data chunks, passing them through our transcription translator, and outputting the formatted result to our caption renderer. Using standard library data structures, this code encapsulates the entire processing cycle cleanly and efficiently. Every robust application must handle edge cases gracefully. What happens when there is complete silence, loud background noise, or a sudden drop in audio buffer delivery? Designing resilient pipelines involves adding silence detection thresholds, fallback states, and exception handling to prevent crashes when audio devices disconnect unexpectedly. Ensuring smooth performance keeps the user experience seamless even under imperfect system conditions. Let's review our final, fully self-contained script. This code integrates our audio simulation, caption renderer, and error handling logic into a single executable workflow. Run this script to see how all the pieces fit together to create a responsive, production-ready foundation for system-wide audio captioning in Python. Congratulations! You have explored the core architecture behind real-time audio accessibility, from understanding system loopback pipelines and managing audio buffers to building rolling caption renderers in Python. You now have the foundational knowledge needed to build powerful accessibility tools. Experiment with connecting third-party speech recognition APIs or advanced GUI toolkits to take your live caption utility to the next level. Happy coding!